Let's get into the first questions. If you see the first question, you will see these two pictures, and as we can guess, the cart X is moving towards the cart Y. And if you see the graph below, we have the velocity versus time graph. And if we see this one, and we'll definitely know that the cart Y is going to collide with the cart Y, and which is going to be a question about the momentum and impulse things, right? So before you start solving the question, you will have the information about this momentum and collisions and impulse things before you actually start with the numbers, right? So in question A, they asked to show that the collision is elastic. Okay, so we have these momentum questions. And they ask to solve if the collision is elastic, which means that we have to show the kinetic energy before collision must be equals to the kinetic energy after collision. That's conditions for the elastic collisions, right? So before collisions, we have to start with the number with the cart X. If you see the question and the mass of the cart is 3 kilogram for X and 6 kilogram for Y, and the initial velocity of the cart X is 6 meters per second, right? So the kinetic energy for before collision is only for the kinetic energy of the cart X, which is equals to half mv squared, and half times mass, which is 3 kilogram, and velocity, which is 6 squared. And now use the calculator. 3 times 6 squared, we have 54 joules for the cart X, and that's the total momentum, total kinetic energy before collision. And let's going to solve this one, kinetic energy after. That is half mv squared of the X and plus half mv squared of the Y cart. And now we have to look at the graph here. And if you look at closely, you will see the number 6, which is 6 meters per second. So this line here is for the cart X. And this one here, start from the 0, and during the collisions, the speed is going to increase and reaches to the 4 meters per second, which is for the cart Y. So after collision, we have to see the number with this one here for the cart X, and number for this one here, which is 4 meters per second for cart Y. So we have to substitute the number half times mass of the X, which is 3 kilogram, times velocity, which is in this case -2. You can substitute -2 or the +2, doesn't matter. And half times mass, which is for Y, is 6 kilogram, times the velocity, which is 4 squared in this case. Just make sure that you use calculator all the times to minimize the errors, which is 6 in this case plus half times 6 times 4 squared, which is 48. So that goes to 54 joules. Then we now confirm the kinetic energy before is equals to kinetic energy after, because they have all 54 joules. Okay, now let's go into the question 1b. In question 1b, they said determine the magnitude of the average force exerted on Y. So they asked to calculate average force. So a student might confuse like how to calculate the average force for each of them. So because we have, if you think about the force wise, we have F equals ma, or they have a lot of like force equations, right? But they have some hints for this. For example, every time when you see the word average force, right? And you should initially think about F equals to delta P over delta T, which is the momentum equation, okay? They are given in the formula booklet. And every time when you see not just force, average force, you have to think about F equals delta P over delta T. Okay, so most of the time, I'll say like about 80% of the time, you will have to use this equation if you see the average force. Okay, so we have to use delta P over delta T, but remember that's the average force exerted on Y. So we have to see the Y things in here. So for Y, we have this graph for Y. And now we have to think about delta P over delta T. So delta P, we have to change delta mv over delta T. And only thing that changes is delta V. So we have to change the equation something like this. And the mass of the Y was 6 kilogram. And now we have to see the delta V. So if you see the y things in here, it starts from the 0, right? Because that was stationary initially, and then that goes to the velocity, which is 4 meters per second. So change in velocity is from 0 to 4 meters per second, which is 4 meters per second in this case, over delta t. So delta t shows the contact time, and it goes from, like, if you see from 0 to 10, that's still 0, but from the 10 here, they start to increase, right? Something like this. So this is the moment they start to contact, okay? And then when they finish the contact, you will see something like this here. They finish the contact, so the velocity of the y is constant in this case. So the contact time for this question is about from 10 to 50 milliseconds, right? So from 10 to 50, so we have total 40 milliseconds in a contact time. So we have the 40 millisecond. So now we have to change the milliseconds to the second. So for millisecond, we have to multiply 10 to the negative 3, right? So if you calculate that one, we have 6 times 4 divided by 40 times 10 to the negative 3. They have 600 newtons. Okay, so that was question B1. So let's move on to the question B2. The question B2, they ask for the average power delivered to Y. Okay, so average power. So if you think about the power equation, we also have two equations to consider, which is work done over time, or you can use power equals to force times velocity V. Okay, so in this case, we need to calculate average power. So if you think about average power, and now you have to think about, like, if I have to use W over T or F over V. But what we can do in this case is, because in question B1, we calculated average force, which is 600 newtons. So now we have the information of the force 600 newton. So it's more likely to use the second question, this one, okay? And now we have to see what's the velocity for the Y. And if you're going to this diagram, we also have to look at the Y one, which is this one here. But now we have to see what's the information for the V, right? But some people might think V is this one, so they use the 4 meters per second. But think about this is the average power, right? So because it's average power, I think we have to use average velocity between 0 and 4, okay? So during this process, we have to see what's the average velocity. So average velocity is, of course, something in the middle. So we have to use 2 meters per second for V, okay? So we have to substitute 2 meters per second here. So that goes to 1,200 watt for question B2. Okay, so the last one, B3, they ask to calculate the elastic energy stored in the spring at T equals to 30 milliseconds. So now we have to see the elastic energy when T equals to 30 milliseconds. Okay, so let's see, like, what's the situations for that. When the 30 millisecond, which is this situation here, the X goes towards the Y, and then they collide, and the spring was like half rotated and half unrotated, something like that, right? So the velocity of the Y was increasing, but not fully, okay? So there was something in the middle. So if we see this question, we have to go through the energy-wise, right? So because we have elastic potential, we want to get elastic potential energy at T equals 30 milliseconds. Let's think about the total energy. So we have a lot of things to calculate how the total energy, but I think the most easy one is when you calculate the initial situations, right? So if you think about the energy conservations, the energy has to be conserved from the initial situations. So initial energy, which is the total energy from the first, is half mv squared, which was exactly the same as the kinetic energy before, which was 54 joules, right? So the total energy in these situations is 54 joules. And this one has to be conserved in any situations, right? So if you think about the situation at T equals to 30 milliseconds, I'll say half, the spring is half loaded and half unloaded, right? So in that situation, we have the kinetic energy and also we have the elastic potential energy. So this thing here is we have the things that we have to calculate, and that has to be 54 joules because it has to be the same. So now we have to think about what's the kinetic energy for these situations. So in 30 milliseconds, if you think about, so in the cart X, they still have some velocity. If you think about this one here, and for cart Y, they also have the velocity of 2 meters per second. Okay, at 30 milliseconds, cart X has 2 meters per second, and cart Y moving in at 2 meters per second as well. Okay, they both moving at 2 meters per second. So for the kinetic energy, we have to think about cart X. Also, we have to think about the cart Y. So that is equals to mass was 3 kilogram and the velocity was 2 meters per second. And also cart Y 6 kilogram and velocity was 2 meters per second. So that goes to 6 plus 12, which is 18. Okay, so now we can rearrange this equation as 18 plus elastic potential energy is 54. Therefore, elastic potential energy is equals to 54 minus 18, which is 36 joules. Okay, let's start with the question 2. And if you see the question 2, you will instantly see this diagram in the middle. And if I see this diagram, I instantly notice that this is going to be the thermal conductivity question because they have the verb, and then they have the inside temperature and outside temperature, and they have the thickness information as well, okay? So this is going to be the thermal conductivity question. I was like 100% sure when I see this question at first, but this is the first time attempted in 2025. Okay, so they don't have any information, they don't have any question like this in a past paper until 2024. So I think a student might be confused because this question was firstly attempted, okay? In question A, they asked to describe the mechanism of the heat transfer by conduction, okay? So we have to explain what's the conduction. I'm not going to write all the details in here, but I'm going to just write the keywords, okay? So in thermal conduction, we have mainly it's happening the solid, okay? And when the solid, if you think about the solid state, the molecules are close to each other. So when the heat is supplied, the first atoms that the heat was applied, the heat, which is the thermal energy, is transferred into the kinetic energy, right? So the thermal energy is transferred into kinetic energy. And the kinetic energy goes to actually the vibrational kinetic energy. Okay, so they vibrate more vigorously and they collide with other atoms, right? So the keywords that you should include is maybe vibrational kinetic energy increased and they collide with other atoms. Okay, so with these collisions, the kinetic energy is transferred from atom to atom, okay, and until it reaches the thermal equilibrium. So I might write until thermal equilibrium. Okay, something like this. So that's the question A. In a question B, they asked to estimate the rate at which the thermal energy leaves the room through the wall, giving the answer with an appropriate unit, they said. So in this one, they asked for the rate at which the thermal energy leaves. Thermal energy leaves. Okay, so if you think every time when you see this, the rate at which or the rate of something, then you have to think about something divided with delta t. Okay, every time when you see the rate at which the rate of something, it's always about something divided by delta t. Okay, in this case, the thermal energy, so this one here has to be q over delta t. Okay, so now we see this equation q over delta t, and if you think about what it is, we will find in the question booklet, which is delta Q over delta T is equals to K times A times delta capital T over delta X, which is about the thermal conductivity equations, okay? So now we have to search for these whole things, then we have to substitute the numbers in each symbols, okay? So for K is about the thermal conductivity. If you see the question, you will see the thermal conductivity of the wire is 1.3, and A is for the area, so that's 18 times delta T is the temperature difference between inside and outside, okay? So this temperature difference. So inside is 22 and outside is 13, so temperature difference is 22 minus 13, which is 9 degree over delta X is the thickness of the wire, okay? Thickness in this case 0.25. So our thermal conductivity is 1.3 times 18 times 9 over 0.25, which is 842.4. Sounds about 842, okay? But in this question, they ask to answer with the appropriate unit, okay? So what's the unit for this delta Q over delta T? If you think about it, it actually, so the upper side here is the energy, right? And this is time. So this is about the energy over time, which is exactly same as power, okay? So that goes to unit of the power, which is the watt. Right, moving on to the question C. If you see the question C, you will have this diagram, and for question C1, they ask to outline why the magnitude of the gradient of the graph decreases, okay? So if you see the gradient initially was great and then it gets decreased, right? So we have to explain why is something like that, okay? So if you see this one, I instantly think about what's the gradient equation. So gradient is always delta y over delta x, right, in the mathematics. If you see what's the y, it's temperature, delta T over delta x, in this case, the time t. So if you think about what's the delta capital T, which is the temperature differences between outside and inside, right? So I'll say temperature inside minus temperature outside over change in time, right? But if you think about this diagram in here, every time when the thermal energy from the inside goes to the outside, you'll see the temperature in the inside will be decreased, right? Because the thermal energy leaves from the room to the outside, okay? So the inside temperature will be decreased every single time over time, right? So the temperature inside decreased, while the temperature outside still remains the same over delta T. So which means that the whole numbers will be decreased, okay? So that's why the gradient decreases. Okay, so you have to explain something like this. Okay, let's move on to the question C2. They said the pressure and the volume in the air of the room remains constant, but the number of molecules has increased. So determine the percentage changes in the number of molecules of the air between t equals 0 and t equals 120 minutes. Okay, they said about the information about the pressure and the volume is constant. Okay, so if you see the pressure and volume, I might think that, okay, so this is about the PV, and the equation related to the PV is equals to nRT, or PV equals nkBT. In this question, it actually doesn't matter which equation to use. However, this nRT for the N stands for the number of moles, and this nkBT, the N stands for number of molecules. Okay, so actually, it's better to use this one because they ask about the molecules, but in this question, it actually doesn't matter. Okay, so I'll just use the first question here because it's simpler. So the pressure and the volume is constant every single time, but we have to compare it when t equals 0 and t equals 120 minutes. So firstly, I'll go with t equals 0, and PV equals to N times R times T. So the temperature we have to use t equals 0 is this one here, which is 22 degrees Celsius, but you cannot use 22 degrees Celsius in this equation because you have to always change to the Kelvin, okay? So that has to be 22 plus 273 in this question, so which goes to 295. So because the information for the N is important, so I will rearrange this equation in terms of N. So N equals to PV over 295 R. So that's the initial number of molecules, right? So when T equals to 120, so the PV equals to, because the pressure and volume is the same, so I don't have to change anything else. So I can just use PV, okay? But in this case, nRT, however, the n number of molecule has changed, right? It has increased. So I'll use n prime in this case, and R times delta T. In this case, the temperature is this one here, which is 6 degrees Celsius, but we cannot use 6 degrees Celsius, right? So you have to add 273, in this case 279. So n prime is equals to PV over 279 R. Okay, so we have two information for the number of molecules. So now we have to change the percentage changes, percentage increase in the number of molecules. So if you think about the percentage changes, it's always change number over the original. Okay, so that goes to, so n prime minus n over n. Okay, so that has to be PV over 279R minus PV over 295R over PV over 295R. Okay, so PV can cancel out, and also R can be canceled out. Okay, so that is 1 over 279 minus 1 over 295 over 1 over 295. Okay, if you use the calculator and then times 100 for the percentage, you will see about 5.73%. Okay, for the question 2D, says that discuss how the second law of thermodynamics applies to the situation of the room cooling down. Okay, if you think about the second law of thermodynamics, it's always about the entropy, right? So for the entropy, I'll say firstly, I'll say the second law of thermodynamics. Okay, the second law of thermodynamics states that the total entropy increases over time, right? And the second things that I would say is as the temperature of the room decreases, right, inside, and their entropy decreases, right? So inside the room, they said the temperature of the room decreases, and so that the entropy also decreases, right? So inside the room, as temperature decreases, then the entropy S also decreases. However, outside of the room, the heat is transferred from inside to outside, right? So outside environment gains the thermal energy. So outside gains thermal energy. So because we have the equation which is delta S is equals to delta Q over T. So when the thermal energy gains, so delta Q over delta T is positive, right? So which is delta S is also positive. So which means that the entropy increases over time. So from this one, we can say the total entropy increases. Right, moving on to the question 3. So when you see the question 3, you will see about this diagram here. And every time when I see this diagram, I will think about okay, that's the uniform electric field. So every time when the uniform electric field is used, the equation E equals to potential difference over the separation D is always used, okay? So question A, say to calculate the electric field between the plate. So they ask the calculate the electric field, but student might think about like what's the electric field? What electric field force, electric field strength, electric field potential energy, what, okay? But every time when they skip the word behind the electric field, it's always electric field strength, okay? So for the electric field strength, E equals to V over D. So as I said, this equation is used. So E equals to V, which is 120 volt, over the distance between the separation, which is 8 centimeter. But centimeter has to be changed into the meter, which is 10 to the negative 2. So if we calculate that one, that's 1,500. For the unit for E, I'll stick with newtons per coulomb. So that's the question A. And the question B, question B1 say to show that the acceleration of the upper particle is about 7 times 10 to the 10 meters per second squared. So acceleration is about 7 times 10 to the 10. We have to show that. Why? Okay. So when I see A, acceleration, I think about F equals ma, okay? And we just like kind of think about, can we actually get the information of the force and the mass? Then we can actually use this equation, right? So if we think about the mass first, they said it's upper particle. You see, upper particle has 2 proton and 2 neutron. And we know the information of 2 neutron and 2 protons mass, okay? However, actually you can estimate this is actually for U, right? So because proton mass and the neutron mass is about the same, okay? So it doesn't have many difference between them. But if you want to make sure with the exact value, you can actually use the proton mass and neutron mass by using this case for U, okay, instead of them. And then how about the force? Can you actually calculate the force? What's the force involving this in this? We have the uniform electric field and the upper particle is accelerated from here to here. What's the force between them, okay? So we have, in this type, we have the upper particle which has a charge. And how about the force in electric field? We have force F equals to E times Q. So I'm going to use this equation here. So I can actually calculate the force and I can actually calculate the mass. Then I can, using this information, I can calculate the acceleration, right? So E was this one here, 1,500. And the Q is the charge for the upper particle, which is 2E. Okay, so now I can set equations, something like F, which was 1,500 times 2E. E is 1.6 times 10 to the negative 19 coulomb, is equals to ma. Mass is 4U. But if you see the formula booklet, and you will see the value of U is 1.661 times 10 to the negative 27. So 4 times 1.661 times 10 to the negative 27 times acceleration A. Okay, so now we have to calculate A equals to, you just have to rearrange this one to the left-hand side. Okay, so just divide by that part, you will see A equals 7.22 times 10 to the 10 meters per second squared. So that's about 7 times 10 to the 10 meters per second squared. Okay, moving to the question B2. In a question B2, they said calculate the time taken for the upper particle to reach the negative plate. So now we have to calculate the time taken t. So just rearrange, just like remind what's the information that we have is actually we have the distance, which was 8 centimeter. So that was 8 times 10 to the negative 2. And now we calculated acceleration A, right? So which was 7.22 times 10 to the 10 meters per second. Okay, you do not use the 7 times 10 to the 10 meters per second square for the acceleration, because that was just a short question in question BI. But you cannot use that one in a following question, okay? Always try to use the exact value. And do you have another information? We have, because that start from the rest, so their initial speed U equals to 0. So if I rearrange this, the quantity that I know, actually, I see, okay, maybe to calculate the time t, maybe I can use the kinematic equation, okay, the Subot equation things. So using the Subot equation, I have information S, A, U, and T. Then I might think about, okay, S equals to UT plus half AT squared. So S was 8 times 10 to the negative 2. U was 0, and plus half times acceleration, which is 7.22 times 10 to the 10, and t squared. So just rearrange the equations, you will get the t, which is about 1.49 times 10 to the negative 6 second. Or you can say 1.5 times 10 to the negative 6 second. Okay, that was the B2. And lastly, we have B3. Say states in EV, electric volt, the kinetic energy of the upper particle when it arrives at the negative plate. Okay. So when you think about the kinetic energy, when it arrives to the negative plate, it's about the energy, right? So from the positive plate to the negative plate, the upper particle is moving from here to here. However, it's about the energy part. So because they said kinetic energy, so student might think about, okay, I can use the half mv squared. But I think the problem is gets harder, and it can be solved in a simple way, because if you think about the energy, it's actually same as work done. Okay, and if you think about the work done in this, the electric field is always same as V times Q. Okay, and we know the potential difference between the plate was 120 volt and the charge in this case, because it's upper particle, we have 2e. So 120 volt times 2e, which is 240 eV. Okay, so we don't have to calculate, we don't have to do the unit conversion every single time. It's just like 240 eV. Okay, so this is how we solve. Okay, now let's move on to the question 3c. And you see this diagram, and then they said the magnetic field is directly into the plane. So now we have the two fields, electric field and magnetic field, at the same time. So most of the time, when you see this diagram, electric field, the uniform electric field normally, and the magnetic field is applied inside. It's about the velocity selector problem. Okay, so velocity selector is something like the particle go in a straight line, so it does not deflect upward or downward. Because if you think about it, because that's upper particle, which is +2 charge, the upper side is plus possibly charged, so the upper particle actually has to be deflected downward because of the electric force. Okay, so electric force applied downward, which is electric force. However, it does not deflect because of the magnetic field. Okay, if you think about the Fleming's left-hand law, and you will see the magnetic force will be applied upward. So because the magnetic force is equals to the electric force, so it does not deflect, it just goes in a straight line. Okay, so they said in question C, calculate the magnitude of the magnetic field. Okay, so now our purpose is to calculate the magnitude of the B, magnetic field strength. So now we have to use the principle of magnetic force is equals to the electric force. If you think about it, magnetic force in a particle, then we have to apply the equation B V times Q. That is equals to electric force, in this case, E times Q. So the Q cancels out. And if we want to calculate what's the B, equals to E times V. So electric field strength was 1,500, and the velocity in this question is given as 5 times 10 to the 5, so 5 times 10 to the 5. So if you calculate that one, the number is 3 times 10 to the negative 3. And the unit for the magnetic field strength is Tesla T. Right. Moving to the question D, they said the upper particle is replaced by the electron. Okay, so now we have electron here, and now we have to draw the path of the electron. So they say, does it go straight line, or does it goes like deflect upward, does it deflect downward, something like that. However, if you think about the formula that we used, so which was electric force is equals to magnetic force. So electric force was towards downward, and magnetic force was towards upward. Okay, so if you think about it, so again, BVQ equals to EQ. However, from the upper particle to the electron, the only changes we have is charge, right? The upper particle has 2e, however, the electron has negative e, right? However, if you think about the equation, Q is always cancels out because they both have the Q at the same time. So it does not matter if the upper particle used or the electron is used, okay? It always has the same value of the upper side and downward, okay? So it always go to the straight line. So you have to draw the line, something like this. Right, let's move on to the question 4. So when you see the question 4 and when you read the question 4, you will instantly know that this question is about the interference and interference patterns, right? So this is about the double slit interference. However, if you read carefully, they said P1 and P2 is where the destructive interference happens, right? So normally when you see the double slit questions, they normally talk about the bright fringe where the constructive interference happens, right? However, this question is something different. In the question 4a, they said explain why the two sources need to be coherent for the interference pattern to be observed, right? So they talk about some things related to coherent light source. So they ask what does it means by the coherent light source, right? So when the light sources are coherent, they said there are constant phase difference in a source, right? So you have to say about the constant phase difference. Okay, so that's the question A. The question B, they have a lot of conditions. For example, the light wave is 720 nanometers, and the two slits are separated by 0.12 millimeters, and P1 and P2s are destructive interference, right? And question B1 say to calculate in radians the angular separation of the pi of the P1 and P2. Okay, so you have to calculate the angular separation of the pi. So I'm gonna just divide into the two parts. So let's say this is pi theta. So if we want to calculate pi, that's the 2 pi prime. So I'm going to calculate what's the pi prime in this case. So in order to solve this type of question, you have to go into more like fundamentalist things. Okay, so because that's if you think about the P1 point, because that's constructive interference, we can think about what's the path difference and phase difference. If you think about the phase difference, because it's the destructive interference, and this is the first point where the destructive interference happens. So that's phase difference should be lambda over 2, right? Where it's the same as pi, like 3 pi, 5 pi, something like that. But because that's the first point, it should be the pi radiance difference. But I can say actually lambda over 2 as well, right? So if you think about the path difference, also you have to know about the knowledge about how to derive this double slit equation, right? So if you think about it, it's actually always d sine theta. Okay, something like this. Okay, so in order to the destructive interference happens, the path difference has to be equals to the phase difference. Okay, so which means that lambda over 2 must be equals to d sine pi prime, something like that. So now let's substitute the numbers, because we have lambda as a 720 nanometer divided by 2 is equals to the separations is 0.12 millimeter. So 0.12 times 10 to the negative 3 and sine pi prime. Okay, so if you calculate this one and just like rearrange this to the left hand side, and then you just like arc sine theta apply, and then you will see pi prime is equals to about 0.00300, something like that. Okay, so which is about 0.003 radians. And then finally we have to calculate the pi, which is equals to 2 pi prime, that is equals to 0.006 radians. Okay, so this is how we solve the question BI. And B2 say that suggests how the energy conservation is consistent with the fact that the energy is at the P1 and P2 is 0. So in question B2, we have to think about the energy wise, right? But at the P1 and P2, they have the destructive interference, which means that their amplitude are cancels out, right? Which means that the amplitude is equals to 0, which means that the energy is equals to 0. So if you compare with the constructive interference, they have more energy there. And if you think about the destructive interference, they have 0 energy there. So the energy conservation is consistent in this case. So moving to the next questions, we have question 4C. They said outline why the interference M is constructive, right? So if you read carefully in the question, they said a beam of the light containing all the wavelengths in the range 550 nanometers to the 650 nanometer incident normally on a diffraction grating. So this question is about the diffraction grating, right? And if you think about the midpoint here, at the midpoint, they always constructive interference. Why? Because there is no path difference, no path or phase difference. Okay, so if there is no path difference or phase difference, that means that they have in phase, right? Because their phase difference is equals to 0, which means that the constructive interference happened. Okay, so that's the question C. And how about the question D? Question D says, determine the largest order of diffraction pattern in which the order wavelengths in the incident beams are present. Okay, they want to know what's the largest order of diffraction pattern. If you go into the formula booklet, you will find out the equation for the diffraction grading, which is equals to d sine theta equals to n lambda. But in this question, they ask what is the largest, what is the maximum number of n. Okay, if you think about what's the maximum number of n, so we have this angle theta here, and let's say this is point n equals 1, like n equals 2, something like that. And if you want to see the largest maximum number of diffraction pattern, it goes the angle towards something like this, something like this. We'll still have some points when there's like a really long words, right? Long screens. However, if you go something like this, and if you actually go beyond the point where theta is 90 degrees, you'll never see any points beyond that, right? So if you want to see the largest pattern, largest number of n, you have to substitute theta equals to 90 degrees. So when the theta is 90, d sine 90 is equals to n lambda. However, sine 90 equals always 1. So d equals to n lambda, therefore n equals to d over lambda. However, lambda is given as a range between 550 nanometer to 650 nanometer. Okay, so we have to actually perform both of the number. So for n, when lambda equals to 550 nanometer, n is equals to d. D was 1 times 10 to the negative 3 divided by the lambda, in this case 550. That is equals to, if you calculate the number, you'll have n equals to 3.13. So n is 3 because that has to be integer number. Okay, so when the lambda is equals to 650 nanometer, so the n equals to 1 times 10 to the negative 3 over, you'll have 650 nanometer, then that is equals to 2.65, so n has to be 2. So now we have to choose n equals 3 or n equals 2, okay? However, if you think about, in the question they said, diffraction pattern in which all the wavelengths in an incident beam are presented, okay? They need to present all the wavelengths, okay? So we have to choose the smallest number in this case here. So n has to be 2 in this case, okay? Okay, moving to the question 5. I think this question students might find particularly hard because this is about the Compton scattering, which is 8.2 quantum physics. And this question is also firstly attempted in 2025. Okay, so in 5A, they say outline why the Compton scattering offers the better evidence for the particle nature of the light than the photoelectric effect. Okay, the difference between the Compton scattering and photoelectric effect is that the photoelectric effect, all the energy from the photon is transferred into the electron. Okay, all the energy. Okay, so that's one-to-one transfer. However, in Compton scattering, not all the energy is transferred to kinetic energy. Okay, some of the energy in a photon is transferred into the electron. However, not all. Okay, so but why it's better? Because we have to state the two part because it's actually tells about the conservation of momentum. So the firstly, we can say conservation of momentum. And the secondly, you can actually say because of the energy transfer, they have change in wavelengths, okay? So because of energy lost in the photon, that means that they have wavelength changes. Okay, so that's an answer for the question 5A. And question 5B said outline why the wavelengths of the scattered photon is longer than the wavelengths of incident photon. Okay. B, I said that because the incident photon collide with the electron. Let's say the incident photon has energy of the 100, right? Let's assume that. However, I said not all the energy is transferred to the electron. Okay, this scattered photon has some of energy left. Okay, so let's say energy is like 30, is left. Then the energy of the 70 goes to the electron, right? Something like that. Then if you see only the photon, it has initially hundreds of the energy, but now we have 30 of the energy. Okay, so the energy has decreased. So I can say some of energy is transferred from the incident photon to the recoiling electron. Right. So which means that scattered photon has less energy than the incident photon, right? So which means that the energy of scattered photon less than the energy of incident photon. And due to the equation E equals to HF, then the frequency of the scattered photon is less than the frequency of the incident photon, which means that finally the wavelength of the scattered photon is now greater than the wavelength is incident photon. Why? Because we have C equals to frequency times lambda, so the frequency and the wavelength is inversely proportional, right? So this is the answer for question B. So moving to the question CI, CI said that to show that the energy of the scattered photon is about 0.17 mega eV. Now, let's try the equation E equals to H times F, Planck constant times frequency. And due to C equals to F times lambda, we can actually change HC over lambda. Now we can just substitute the numbers, right? So H is 6.63 times 10 to the negative 34 times the C, which is 3 times 10 to the 8 divided by lambda in this case is 7.47 times 10 to the negative 12. It is given in the questions, right? And if you calculate that numbers, you'll see 2.66 times 10 to the negative 14 joules. Okay, now we have to change it into the EV, right? So if you want to change it into EV, we can simply divide by the charge of E, right? So which is 1.6 times 10 to the negative 19. Okay, so that is equals to 0.17 mega eV. So that is equals to about 1.66 times 10 to the 5 eV. So that is actually equals to 0.17 mega eV. Okay, that was the question C1. And moving to the question C2, they said calculate the kinetic energy of the recoiling electron. So this question is particularly so what I can do in this question is that if you see these numbers here, in question CI, we calculated the energy of the scattered photon, which is 0.17, right? So the scattered photon energy was 0.17 mega eV. And we want to calculate what is the energy of the recoiling electrons, right? Then what we can do is we can actually calculate the energy of the incident photon, and then we just like subtract from that, right? However, the incident photon's energy is given in a formula, given in the questions, which is 0.194 mega eV. Okay, so then the recoiling electron's energy is this number 0.19 mega eV minus 0.17 mega eV, right? So that is equals to 0.194 mega eV minus 0.17 mega eV. So which is equals to 0.028 mega eV as the answer. Okay, lastly, we have question C3. They say for electron, H over ME C is given as 2.43 times 10 to the negative 12. So that is given. So they say determine the theta. Okay, they want to calculate the theta, which is in this case this one here. So every time they ask the angle, we have to think about this equation here, which is given in a formula booklet. So that's delta lambda change in wavelength is equals to H over ME C times 1 minus cosine theta. So this, again, this equation is given in a formula booklet, okay? So change in wavelength is, if you see the questions here, and we'll know that the initial wavelength was 6.4 times 10 to the negative 12, and then scattered wavelength is 7.47 times 10 to the negative 12, okay? So the changes is 7.47 minus 6.40 times 10 to the negative 12 is equals to, so this number is given in the question here. So 2.43 times 10 to the negative 12 and 1 minus cosine theta. So that's all number now. So you just have to rearrange them, and then if you calculate the cosine theta is equals to 0.5596 blah blah blah. So now we applied arc cosine, that is equals to 55.67. So it's about 56 degree. Right, moving to the question 6. If you see this diagram, you will instantly know that that's the relativity questions, right? I think the relativity is the hardest part in 2025 syllabus. And I'm sure that these questions find it really hard among the students. So there are a lot of conditions for this question. They said the spacecraft S leaves the Earth with the speed 0.6 c on the way to the planet P. So as measured by the Earth, the P is distance of the 30 light years from the Earth, and blah blah blah. And they said question A, S arrives at P after 50 years according to Earth. So calculate the time at which the S arrives at the P according to the S clocks. Okay, so they said between the one frame between S and P, they have 50 years of the time it takes from to the Earth, right? However, we have the different frame of according to S clocks, right? So now we have to think about the relativity effect. And they said the the spacecraft S has a speed of 0.60 c. Then we have to calculate the effect of that speed, right? So now we have to calculate the gamma, which is equals to root 1 minus v square over c square. So in this case, root 1 minus v, which is 0.60 squared, and c squared over c squared. If you calculate using the calculator, you will have 0.8 as gamma. So now we have to see what's the time changes between two frames. If you only compare two frames, you can use the time dilation, okay? So the t is equals to gamma t0. And they said it takes about 50 years according to the stationary frame, which means that we can say t is equals to gamma, which is 0.8 times 50 years. Then that is equals to 40 years. Okay, so that's what question A is. Okay, moving to the question B1. So B said when S arrives at P, so S sends a radio signal back to the Earth. So draw on a space-time diagram the word line of the signal from when it is emitted until it receives on the Earth, they said. Okay, so they said initially when S arrives at P. So when S arrives at P, we have, they said as a time, it takes about 50 years. So when the time was 50 years in here, however, the x-axis in this case, in a question, they said is 30 light years. So that should be about here. right? So which means that that goes to this line. So this line is when the S arrives at P, right? So when S arrives at P, the S send a radio signal back to the Earth. So because the radio signal is the speed of light, right? So when we have to draw the speed of light, you have to always draw the 45 degrees things, okay? So you always have to find the 45 degrees. You should draw in this direction. Also, you should draw this direction as well, okay? So this direction, because you never know which one actually crossed the line, okay? So if I try this line first. So the 45 degree is something like this line. However, it never cuts the line of the Earth, which is the X and CT prime, right? So I have to draw the another line, which is the 45 degree to downwards, something like this. Something like this, okay? That's bad drawing. Something like this. But now you see like it actually cuts the 80 years of the time frame, right? So you have to show these things in here. So you can actually like remove that line, and then you can just only remain that line. Okay, so this is how we solve the question B1. And question B2, they said determine using the space-time diagram or otherwise the time of the travel of the signal according to S. Okay. So I solve in here. Right. So now we have to use the time of travel of the signal according to S. Okay. So the time of travel, so if you think about the first time frame, X1 and let's say CT1 frame, they have now the firstly 30 years, 30 light years and 50 light years, right? And then it goes to X prime and CT prime frame because the S is moving the spaceship, right? So I'm going to go X1 prime and CT1 prime, okay? Then it will show this point here. And also, so that means that the X1 prime is 0. And we calculated CT prime, CT1 prime in a question A, right? It was 40 years, right? So that's 40 years. And now let's think about, so this is when the signal goes from, when the signal goes, right? So when the signal is sent back to the Earth, that's, let's say that's X2 prime. So X2 and CT2, okay? So it took about 80 years, right? So that was like, if you think about this line here, because if you think about that line here, because we are thinking about the time, so it took about 80 years. So that line is 0,80 light years, okay? But now let's think about when it goes to the moving frame, which is X2 prime and CT2 prime. Okay, so that goes to, so we actually don't care about X2 prime because that's the position, right? So we only care about the time it took. So in that sense, because moving back to the Earth and that's light, the light cannot be faster than the speed of light, right? So the time taken has to be slower, okay? Because in a time frame of the S, we know the time frame has to be changed, right? So either we can use the t equals to gamma t 0, but if you think about it, because the radio is already reaches to the speed of light, it cannot be faster. So the time should take longer, okay? So it should be 80 light year divided by 0.8, which was the gamma, okay? So it should take 100 light years. So at firstly 40 years, and then we have, it took 100 light years, which means that the time of the travel of the signal according to S should be 100 light year minus 40 light year, which is about the 60 light years.